The broadcast is now starting. All attendees are in listen-only mode.
Good morning and afternoon, everybody. My name is Janie Montblanc, and on behalf of the Great Basin Science Delivery Project PIs and partners, we welcome you to the 5th webinar in our Sagebrush-Steppe Treatment Evaluation Project series titled Hydrologic Response to Fuels Treatments on Woodland Encroached Sagebrush-Steppe, presented by Jason Williams from the USDA Agriculture Research Service. This is the Science Delivery Project's final webinar of the season, but if you're on our listserv, I will periodically send updates about relevant webinars from partner organizations. Before I introduce our speaker, I want to let you know that you may ask questions at any time during this webinar by typing them into the questions pane of your control panel at the top right of your screen. I will field questions for Jason after the presentation. I also want to give you a heads up that during the questions period, I will be submitting 3 brief poll questions about the webinar. Your input is greatly appreciated. Thank you. Now I would like to introduce our presenter. Jason Williams is a hydrologist and support scientist with the USDA Agricultural Research Service Northwest Watershed Research Center in Boise, Idaho. His work with Dr. Fred Pearson at NWRC investigates rangeland hydrologic processes and the hydrologic impacts of rangeland restoration practices and wildland fire. Welcome, Jason, and thank you for being here today.
Well, thanks. As I get started, we'd also like to recognize the other co-authors that helped me put this together. Those are Fred Pearson, who's the primary investigator for the hydrology component of SageSTEP, and then Dr. Osama Al-Hamdan, who's a postdoc researcher here with us. And he's now taking much of the data you'll see today and trying to develop model parameters for the rangeland hydrology and erosion model. And I'll talk briefly about that. And then Patrick Kormos, who collected much of the data that you'll see here. And the general theme that we'll operate under is to look at these cross-scale pattern process relationships for Sagebrush-Steppe and Woodland Encroached Sagebrush-Steppe. And by that I mean how runoff and erosion processes at fine scales, how they parlay into what's happening over larger scales. And we'll be looking at small plot rainfall simulation and large plot rainfall simulations to do that. But what we know from literature, history, and even from the data that we'll present today is that for these stable communities with heterogeneous soils and vegetation, runoff and erosion are generally quite low. There's high infiltration rates under the shrub canopies or grass canopies, and then low runoff and erosion from those locations, and then high runoff and erosion from the bare patches in between shrubs and grasses. But the erosion here is generally by rain splash, and it's a very inefficient transport mechanism, so the soil travels a very limited distance before it's captured and trapped by the vegetation on the site. So for these conditions, we generally think of them as being hydrologically stable, and we see decreasing runoff and erosion with increasing area. As we shift over to a more degraded state where we have large connected patches of bare ground with low infiltration rates, runoff at small scales tends to amplify over larger scales, and we see formation of concentrated flow paths that are able to transport the rain splash sediment a greater distance than just from rain splash processes alone, and also are eroding from within the channels that they create. And so under this condition, we generally see an increase in erosion and occasionally runoff over larger scales. So it's really about looking at how processes across scales change and what that might tell us about the ecological state. We can think about that in terms of a model to look at woodland encroachment into Sagebrush-Steppe. And as we look at this gradient and vegetation change from, say, a Sagebrush-Steppe site to Phase 3 woodland with these large patches of bare ground, we can see how the process changes, as we just discussed, from rain splash to sheet flow. And this is just a conceptual model here that we would see low erosion, and at some point there's a threshold change where concentrated flow takes over, and we see exponential increases in erosion over larger spatial scales. And one of our main questions is, where does this threshold exist along the encroachment gradient, and is it reversible? And we'll be looking at that specifically in terms of these treatments: burning, cutting, and mastication. So are they ecohydrologic reversal mechanisms, or ways in which we can move from, say, phase 2, phase 3, and shift into this direction in our model back to a sagebrush-steppe environment dominated by rain splash and sheet flow. So the vegetation is having a great influence on runoff and erosion behavior, and we're interested in what these treatments here may do in terms of our model and erosion. And the way we investigate this in our sagebrush-steppe sites is to go out and conduct rainfall simulation at large and small plot scales. On the left, you can see here, this is our small plot rainfall simulator, and we conduct these simulations over a ½ square meter, typically in interspace areas, and maybe another plot would encompass an entire shrub, and then also we have vegetated interspace areas as well as tree coppice areas, and I'll show you some pictures of those in a moment. And then we have standpipe rainfall simulations over areas of anywhere from 13 to 35 square meters. These plots are generally telling us what's happening not only at these finer scales, but also what happens when concentrated flow occurs. So the small plots are aimed at rain splash and sheet flow erosion, and the larger plots are aimed at quantifying those processes as well as concentrated flow. In addition to rainfall simulation, we also release concentrated flow at the top of our plots after doing rainfall simulation. This is aimed at really getting out the numbers for specifically for erosion created by concentrated flow itself, not including the rain splash component, but just erosion by the flow itself. And then we spend a great deal of time characterizing our plots, measuring ground cover, canopy and basal gaps, soil stability, water repellency, and other measures, also that we can relate the runoff and erosion measurements back to the characteristics on the plots and across our sites. In SageSTEP, we have 3 of what we are referring to as our hydrology study sites. Again, here we're just looking at overland flow processes, so not other hydrologic variables like transpiration or evaporation. We're just focused on overland flow here. We have 3 sites: a western juniper site in southwestern Idaho. We have a Utah juniper site in northwest Utah, and then a pinyon juniper site in east central Nevada. And you can see that if you look at the characteristics for the sites, they're generally in the frigid to mesic environment, and they're typically on the threshold of aeritic to xeric, so right on the fringe of those 2 moisture regimes. I'll also talk about some data from other rainfall simulation study sites that we have across the Sagebrush-Steppe to Woodland domain. There's about 10 sites in total, from loam to sandy loam soils, and you can see the numbers here for the SageSTEP study plots. 150 large plot rainfall simulations and almost 400 small plot rainfall simulations. But then also, if you combine our data from the other study sites, we're somewhere on the order of 200 large plots and almost 900 small plots. And in many cases, these numbers, probably 50% of these plots, we ran simulations at 2 different intensities. So we're talking about a large number of plots here from which we're trying to draw inferences. So we'll start looking at some of the data now. These are small plot rainfall simulation data, and I've shown the microsites on the bottom of the slide here. On the far left, this is, of course, the bare interspace area. In many cases, we might have 20% cover in these interspace plots as well, and then the shrub and the tree coppice plots. And you can see the runoff and erosion numbers here. These are means across our marking corral and Onaqui sites from small plot rainfall simulation. And in general, what we can see if we look at this graph on the left, runoff versus litter cover, as you would expect, these interspace plots are producing most of the runoff and erosion at the small plot scale. This graph on the left is just runoff, and then this is erosion here. Once we get into the shrub coppice area, runoff is quite low, as is erosion, and then we see an increase in runoff for these tree coppices. And this is largely because of the water repellent soils underneath 5 to 10 centimeter thick litter mats. Soil surface is strongly water repellent there. We do cut trees down before our rainfall simulation, so interception would probably reduce the amount of runoff if the trees were still there. So soil water repellency isn't really a great concern for this unburned condition, but later when we get into the burn, we'll talk about its effect there. And again, you can see the decrease in erosion as we increase in cover. All that might be what we would expect, and the main take-home here is that at the fine scale, we're really seeing rain splash and sheet flow erosion from these interspace areas, and we have strong water repellency here underneath the cover, the layer cover. Here's some of the soil water repellency data that we have across our 3 sagebrush or SageSTEP sites. On the left, this is our Utah juniper site, and you can see that anything over 60 would be strongly water repellent, and we had strongly water repellent conditions for each of the 3 years that we went out and measured water repellency. This is again under an unburned condition, and these trends were consistent across all of our woodland sites, and this is data just from underneath the trees. Our sagebrush coppice plots and our interspace plots were all wettable at the soil surface. So now we'll shift gears and talk about large plots. So we're starting to look at a coarser scale, so integrating the sheet splash processes with concentrated flow. And we can see that if we look at this relationship of runoff versus erosion, we had a linear relationship through all of our data, and that these trees represented by the triangles here are the hydrologically stable places on the landscape as you would expect. Rain splash is a dominant process there. As we shift into the shrub interspace zone between the trees, we have these patches of bare ground that facilitate concentrated flow, and we start to see the increase in runoff and erosion. Looking at the lower graph, erosion versus bare ground, we can see that there's this threshold here of about 60% cover where we see this exponential increase in erosion. And this threshold has shown up in almost all of our data across Sagebrush-Steppe and even into the woodlands. So we've seen this consistently, and it's pretty consistent with historical literature, that there's a threshold somewhere in the 50 to 60% bare ground for these exponential increases in erosion. And again, these are associated with a shift from rain splash to concentrated flow as the dominant erosion process. The different colors represent the different sites, so there is some between sites variability. And so this shift generally occurs at 60%, but the magnitude of the increase varies with site-specific soil erodibility. So one of the things we're interested in is how do our measurements at the small plot scale transfer to larger scales, and we can do that by weighting our small plot results into large plots. And what that will tell us is whether this system is moving towards that threshold for increasing erosion with increasing land area versus a more stable condition where soil erosion is attenuated at the landscape scale. And when we did that, we found that the runoff measured at the small plot scale was pretty similar to that at the large plot scale, but was a different story for erosion. And that's what this graph here is depicting. So if we look at marking corral, and we see these red bars here for each of the sites actually is our weighted small plot data put into the same area as our large plots versus what we measured on the large plots. And we can see that erosion was substantially higher at the large plot scale than the rates we measured at the small plot scale. So that would tell us that for these 3 woodlands, they've shifted into this rapidly eroding state, or a state in which erosion is amplified with increasing spatial area, at least over the size of our plot scales. When you combine our paired plots, we're talking about something on the order of 30 to 50 square meters for paired large plots. And so the real question is, have these sites reached some threshold to where our erosion processes now are in this exponential shift? And at least these data would suggest that for the woodlands we looked at, this is occurring. Our sites were generally in late phase 2 to early phase 3, so indicative here by this large red oval. And the data would suggest that if these sites were left as they are, they could potentially shift even more into phase 3, and we would expect erosion to continue to increase. So these sites are what would generally be referred to as a rapidly eroding sites for woodlands. And again, it's associated with the change in the plant community and how that affects these hydrologic and erosion processes. So now we're interested in looking at how the treatments affect the runoff and erosion that we measure. And this is a picture from the Onaqui site, and you can see that in the woodland here, if you look closely, there's less cover in there than there is over here in the cut area. So we would expect this vegetation change to influence runoff and erosion, but there's also an effect of having these trees laying on the landscape, perhaps entrapping soil as it moves down slope. And so we would think of these effects as being short-term effects and these being more the long-term effects. And so we can look at results or the effects of these trees by looking at our short-term data from Onaqui, and then we have another ARS site where we measured runoff and erosion in the Steens Mountains in Oregon, where we'll look at the long-term effects of this vegetation. And what we see from our large plot data, this is actually at Onaqui, Marking Corral, and Castlehead, just throwing these trees into the interspace or cutting trees and allowing them to fall into the interspace had very little or minimal impact on runoff and erosion. So they're shown here by the open circles in this data. And what we can see is that they plot in similar space as runoff and erosion for the plots without the trees laying across them. Same thing can be said if we look at percent bare ground versus erosion. This is bare ground before the trees were laid into the plots, and this is bare soil and rock cover. So when I say bare ground, we're talking about bare soil as well as rock cover. And we can see that they're plotting in the same space in terms of the amount of erosion with respect to the other shrub interspace plots. So really a minimal effect of placing the tree into the interspace area. And it's largely associated with the amount of bare ground that remains upslope of the trees. What we observed is in the shrub interspace zones, when we did our concentrated flow experiments, we measured 5,600 grams of erosion. With the trees across the plot, we did see a 1,000 gram decrease, but these two numbers were not statistically different. And what we observed is water above the tree formed concentrated flow paths that were able to work their way through this tree material and still generate a substantial amount of soil loss at the plot outlet. So those are the short-term results. So now we'll look at some long-term data that we have from Steens Mountain, and we'll look at rainfall simulation as well as concentrated flow data. So Fred Pearson conducted some rainfall simulations at western juniper woodland. This is in the shrub interspace zone between the trees at the woodland site, and then immediately adjacent to that site, this is what we saw 10 years after the trees had been removed. So this is in what was the shrub interspace. At the time it was a woodland, and this is shrub interspace in the adjacent woodland. And what we saw there is that runoff and erosion were negligible from the treated site with respect to the existing juniper woodland. These are concentrated flow experiments at the same site. And again, thinking back to our model, we were in, say, a phase 3 juniper woodland at the time of the experiments, 85% bare ground in the shrub interspace zone between the trees, and we measured 145 grams of soil loss. Conducting the same experiments on plots 10 years post-cutting, 60% bare ground, 45 grams of soil loss. So you can see there's been a shift in the plant community, increasing cover and decreased soil erosion by concentrated flow. And in actuality, the flow was starting to spread out and behave more like sheet flow and less like concentrated flow. 20 years after cutting, bare ground was reduced to 40%, and soil loss was 20 grams. And in this case, we're starting to shift more towards the Sagebrush-Steppe end of our model. Well, now we'll look at some data from Onaqui from mastication. And if you look at the picture, you can see that the shredded material was spread out throughout the site. There are some isolated patches of bare ground, but in general, material was spread into interspace, but there remained quite a bit of masticated tree material still on the coppice mounds themselves. And we'll look at the effects of that here from our small plots. Again, before the treatment, the shrub and tree coppice plots generate very little runoff and erosion. Interspace plots generate 23 millimeters to 52 millimeters runoff, depending upon how much cover there was. And you can see that's a big difference from our coppice or vegetated plots. And erosion was substantially higher, 133 to 313 grams per square meter. Spreading the masticated material into the interspace area reduced runoff to about 11 millimeters and erosion down to about 39 grams per square meter. And as I said, there were some isolated patches of bare ground, and in some cases there was some tracking from the equipment, and that increased runoff and soil loss for these, at least for these bare patches. But again, given the heterogeneity of the site after the treatment, these isolated patches are probably not a major concern. And this work was put together by Nathan Klein, and he has a master's thesis and also a paper in Rangeland Ecology and Management that detail these results. So in summary, for the mechanical treatments, do they represent an ecohydrologic reversal mechanism? And at least the short-term results for the masticated site would suggest that yes, we're reducing runoff and erosion. Processes are shifting more to these sheet splash or sheet flow and rain splash processes. And the long-term results from the Steens site would suggest that we can reverse these phase 3 or late phase 2 woodlands back to a sagebrush-steppe community. Of course, there's probably going to be re-entry to remove trees that were missed during the treatments, and so the long-term results, at least from the mastication and the cutting at the sagebrush or at the SageSTEP sites, will be interesting to track over time. But the long-term results do suggest that we can achieve success in reversing the hydrologic processes if we can get that vegetation response that we observed at the Steens. So now we'll examine wildfire as an ecohydrologic reversal mechanism. We'll look at the Castlehead site. This is a SageSTEP site. This site burned as a part of the Tongue Complex fire in 2007. These are some results at the fine scale, so from our small plot rainfall simulations. Again, these are the stable places on the landscape, the shrub coppice and tree coppice areas. After burning, the shrub runoff from shrub coppices was about the same as before the fire, probably because we didn't see a big change in bulk density. Runoff was quite low. It's pretty amazing how much you can rain on these shrubs before you see runoff. But we did see an increase in erosion from 6 grams per square meter to 56, and a much greater increase for the shrub coppices. Again, this is associated with soil water repellency underneath the litter. If we look at specifically at water repellency, so I know this is somewhat of a confusing graph to look at, but this would be at the soil surface, 1 centimeter down, all the way down to 5 centimeters. And this is for the unburned tree coppice plots. This is 1 year post-fire on the tree coppice plots, and this is 2 years post-fire on the tree coppice plots. And we can see that after fire, it was still strongly water repellent underneath the litter, or at the soil surface rather, or at least in the upper 4 centimeters. It was pushed down a little bit relative to the unburned condition, but it persisted through 2 years post-fire. That was pretty consistent across all of our sites. This is the Onaqui woodland and the Marking Corral woodland site. Same trends there. Water repellency persistent post-fire, at least through the 2 years that we studied. So we'll now shift and look at how those small-scale processes affect things over larger scales, or at least in our large plots. And these are graphs we looked at previously where we saw these linear relationships in runoff and erosion and exponential changes in erosion at this threshold of 60% bare ground. We'll now look at this in context with the burn plots. And what we see from the Castlehead data is there's an exponential deviation from this runoff and erosion relationship. And so after burning, these stable places on the landscape become those where we measured the highest erosion rates. runoff was similar for the burned shrub interspace as the unburned shrub interspace, but erosion was amplified. And so burning, at least in the short run, has increased our vulnerability to soil loss. And we can look at the specific means for these plots. You can see that bare soil increased from 18% to 73% post-fire on the tree coppices. You can see the increase in runoff, about a 4-fold increase, and about a 20-fold increase in soil loss. Burning had very little impact on the interspace plots in terms of runoff, but we did see a 2- to 3-fold increase in soil loss. So looking at the first year data, so this is 1 year post-fire, again area weighting our small plots into our large plots, we saw that there was very little difference in runoff measured at the small plot scale versus the large plot scale. Maybe slight increases, but probably not statistically different for the burned tree and burned shrub interspace zones. But it was a different story altogether for erosion. Erosion was substantially higher for the large plots than the small plots, the rates, suggesting again that we've taken an already rapidly eroding condition, and essentially the fire has made that condition worse. But there's an upshot to this. Those are the short-term results the first year. As you would expect, your vulnerability would go up immediately after burning. But 2 years later, we did see about a 50% decrease in runoff from our small plot rainfall simulations for the interspace areas. The shrubs produced the same amount of runoff and erosion, the burned shrubs did, as the unburned shrubs. We did still see elevated runoff and erosion from the tree plots. There was 23 millimeters of runoff from tree coppices that were burned relative to 8 for unburned tree coppices, 62 grams per square meter soil loss for burned trees versus 5 grams per square meter for unburned trees. But we did see these increases in the interspace area, which is good to see. And we can now look at the effects on the concentrated flow erosion, and these are even more encouraging. You can see that erosion from the unburned shrub interspace 2 years post-fire, so this is just looking at the unburned area, but 2 years after the fire, there's 5,600 grams of soil loss from our concentrated flow experiments. The burned areas 2 years post-fire, we only got about 400 grams of sediment off of those plots. So we can see the effects of this vegetation in terms of breaking up concentrated flow and dispersing the flow across the plot and reducing the amount of soil loss. And so these unstable areas in the landscape are now starting to look a little bit better, and there's reduced soil loss from them. The tree coppices, on the other hand, seem to be taking a little bit longer to recover. Matt Madsen from ARS and Bruce Roundy, who gave some other talks in this series of talks from SageSTEP, they've done some work on this, looking at the effects of water repellency, and that perhaps it might be affecting the vegetation response and causing a delay in vegetation recruitment on these tree coppices. But the hope is that as that soil water repellency breaks down over time without the organic material to promote it, we might start to see good plant recruitment in the tree coppices, and then we would have substantially improved the site relative to the unburned condition. So now I'll look at some data from ARS from a Sagebrush-Steppe site that was burned in the Reynolds Creek experimental watershed. This is a fire, the prescribed fire by the BLM in conjunction with research with the Northwest Watershed Research Center. And you can see that this is the early phase 1 encroachment of juniper into Sagebrush-Steppe. These are some results from the small plot simulations. If we look at infiltration here, the black and blue lines, these are the year of the fire. The blue is for unburned tree or shrub coppices in this case, and from interspace areas in this case. We can see the fire had very little effect on infiltration from the interspace zone, but it did decrease infiltration for the shrub coppices. Another interesting thing to look at from the data is the effect of water repellency. We can see if we look at these blue and black bars, these are the strength of soil water repellency the year of the fire. And we can see that when it was strong, infiltration was far less for both the burned and unburned condition. 1 year post-fire, we can see that there's very little fire effect, but the effect of water repellency is the difference that you see here between the two bars. But shifting now to the large plots for the same site, we can see how the fine scale processes parlay at the larger plot scale. We can see there's about a fourfold increase in runoff from our large plot simulations, again associated with strong water repellent surface conditions and formation of concentrated flow within these large plots. And we see this threshold in bare ground again at about 60% bare ground. We had exponential increases in erosion, and with the highest erosion immediately after the fire, and then decreasing to about pre-fire conditions within about 3 growing seasons. This is how the vegetation changed at the site 1 year and 3 years post-fire. You can see this next slide, we'll see how the changes in vegetation affected erosion. We can see that immediately after the fire, you can see 80% bare ground. We had almost 1,000 grams per square meter of soil loss from our large plots. 1 year post-fire, that was down to 300 grams per square meter with 60% bare ground. And then we're back to kind of pre-fire conditions once we reached 40% bare ground. Some additional data from another site in the Reynolds Creek Experimental Watershed. This was a Sagebrush-Steppe site that was burned. Very little effect on runoff from shrub coppices, but we did see a tenfold increase in soil loss and similar magnitude increase in soil loss for the shrub or for the interspace plots, and an actual decrease in runoff. And that was associated with changes in water repellency. If we look at these data here, water repellency from the same site for the unburned shrubs, it was high before the fire and persisted after the fire, but it actually went away after the fire for the interspace areas. So we think this might be why we see this increase in infiltration, decreased runoff 1 year post-fire from the interspace zones. So what all these data tell us a little bit is how we can look at processes of these fine and coarse scales and what that might tell us about how a system is responding and how the plants are starting to dictate hydrologic processes. And what I'm commonly asked is how do these small and large plot results, what do they tell us about what's going on at larger scales? And so I just threw this slide in to talk about that briefly. We conducted similar simulations in the Boise front, and this was after the 8th Street fire that happened in 1996. And then 1 year after the fire, there was a 9-minute natural convective storm that caused flooding in northeast Boise residential areas. And when the researchers went back in and looked at what were the driving factors for that response, it was associated with the same things we observe on the plot scale. Increased rain splash at small plot scales, increased runoff at small plot scales that resulted in concentrated flow over larger scales, driven in part by soil water repellency, and then formation of these highly erosive concentrated flow or rill networks. Estimated expenditures were over $4 million after this event associated with additional mitigation and treatments. So back to, I guess, our main question is, can fire be an ecohydrologic reversal mechanism in these woodlands? And at least the data that we've looked at from the SageSTEP sites, and then data from earlier encroachment in some of our sagebrush sites in Reynolds Creek Experimental Watershed, we can see that the long-term answer is potentially yes, at least for some sites. In the short run, we might see an increase to the right side of this model where we'd have an even greater degraded condition and concentrated flow being the dominant process and accelerated erosion. But at least it looks like within 2 to 3 years, we can have these positive responses where we have a shift back to rain splash or sheet flow dominated processes and lower runoff and erosion from these sites. Of course, this is going to depend a great deal on site-specific conditions, what kind of plants were there before the fire, what the likelihood of recruiting perennial grasses and ground cover, what's the likelihood of getting those back after the fire, and a lot of that's going to be a function of what was there before and then also what kind of weather you get after the fire. So it looks like, at least in some cases, and in our sites that are highly productive, so early or late phase 2, early phase 3 is potentially reversible back to the conditions we would see for sagebrush-steppe, and that's largely associated with the changes in the plant community after the treatments. So by way of summary here, you can see that the effects of encroachment are strongly dependent on the development of extensive bare areas, and the magnitude of the change when you have woodland encroachment into sagebrush-steppe in terms of erosion is going to be dictated a great deal by site-specific erodibility. We could expect to see runoff or particularly erosion increase once we exceed some threshold in bare ground of about 60%. It seems like at that point there's greater connectivity across at least our plot scales that results in exponential increases in erosion. And then the short-term effects of tree cutting appear minimal, at least from the data that we have, but there are some long-term benefits as represented by the data we presented from Steens Mountain. As we saw from our data, burning increases runoff and erosion, more so from these tree coppices 4 to 22-fold in the data we presented, at least in this immediate post-fire period, so 1 year post-fire. And that burning has a minimal effect on the runoff from these interspace zones, but erosion can increase there as well. But all of this really is to say that these short-term increases in vulnerability are probably worth long-term reductions. Again, our major goal with the model is to shift things back this direction. If these woodlands that are already at some tipping point are left to persist as they are, at least those with high site erodibility, the long-term erosion is going to be substantially more than any short-term increase we might have from a fire treatment. So fire may be a good way to go if we feel like we can get the right plant community response that's going to then affect these runoff and erosion processes in a favorable way. So in addition to what we're learning about these systems, we're now starting to take these data and populate the rangeland hydrology and erosion model. This is a model that's available on the web. If you just do a search for RIM and ARS, it should come up, but it's housed by our Tucson ARS location. And the data from the SageSTEP study are actually going into this model now to populate it. This is a model that originated in some pieces, at least, from the WEP model, but it's now entirely based on rangeland data. And it's a unique model in that context. And it's available for use now on the web. And with that, I'll take any questions.
Great. Thank you so much, Jason. All right, the first question is from Michael Lesky. He asks, it appears as a site progresses towards a vegetative climax state, erosion increases. Therefore, what would be a preferred method to maintain the site at an intermediate successional stage? And he follows that up with, well, I'll just ask the second question later.
Okay. Well, there's a lot to the question, and you know, some of that's probably beyond my expertise to an extent. I'm a hydrologist, not a plant ecologist, but I think what we can see in these data is that, you know, the runoff and erosion responses are strongly linked to vegetation, and we've known that for quite some time. So really, in terms of monitoring or managing vegetation to achieve desired responses in terms of runoff and erosion, requires some understanding of how the plant community is going to shift. So if we're talking about state transition models, that might be something to look at. But you need to know something about how the plant community is going to change.
Hey,
and then
Jason,
look at different.
You're good now. You went quiet for a little bit, but you're back to being good.
Okay. And so then we can look at runoff and erosion for these different types of conditions, and then kind of scale our management of the plant community to line up with that.
Okay, thanks. And then he asks, within the mastification process, what was the mortality index of the associated grasses?
Yeah, that's probably a better question for Bruce Roundy. I think they've been tracking vegetation at the Onaqui site for quite some time, and I don't really know the answer to that question.
Okay, so Michael, if you want to give me an email, or actually I have your email, so I can forward you Bruce Roundy's contact information. All right, Jed Sondergaard asks, what is the history of grazing on these sites?
Yeah, that's a good question. And I don't know off the top of my head what the history of grazing is on the sites. I know it was excluded for I know it was excluded for a substantial period before these experiments were conducted, but I don't know the specific details about each of these sites.
Is there some way someone could find out?
I would suggest Jim McKeever is probably the best person to contact.
Okay.
And then there are different site managers for each of the sites that probably have the detailed information on the grazing regimes. But Jim could put an individual in contact with who they would need for a specific site.
Okay, thanks. So Jed, I'll email you Jim McKeever's contact information. All right, Michael Lesky asks, what was the application rate of simulated rainfall? Was there a rate threshold where soil erosion accelerated?
Yeah, that's an interesting point in that these are isolated, well, I shouldn't say isolated, these are static intensity storms. So we did two application rates. We used what we call our dry run on dry conditions. That was 64 millimeters per hour. And then we had a wet run of 102 millimeters per hour rainfall intensity that was applied on the same plot after running the 64 rate. So we have two intensities, and it's probably really, someone looking at these numbers should probably focus less on the specific runoff and erosion numbers, but the magnitude of differences for the different conditions, which is really telling you a lot about the processes and what's dictating the response. But in this case, for the data you saw today, there were two intensities, 64 millimeters per hour, and then most of the data I presented was really from the wet run of 102 millimeters per hour. And there was a big difference in those responses. So somewhere between those two is where you would see a major shift.
Great, thanks. Devin Comstock asks, have the effects of microbiotic crusts on infiltration rates and erosion been considered in this or other USDA hydrologic studies?
Yeah, I think there have been other studies that have looked at that. It wasn't an issue on these sites in that most of our plots we didn't see evidence of substantial crust development that might affect the infiltration. But there has been work done on that, but none associated with this study.
Okay, thanks. Diane Hopster asks, will this presentation be available after the webinar? Oh yes, it will. I can answer that. I'll give you more information about that in a second. Diane also asks, how do long-term effects from burning compare to long-term effects from cutting? Does one have more impact than the other?
Yeah, I would say that I don't think we really know that, and that's something that would be nice to follow with these studies at these sites. Right now what we're looking at from this study alone are just short-term results, and I don't know of any long-term studies like this for sagebrush systems in particular, or woodlands that are well replicated, where they look at runoff and erosion and infiltration on, say, a burned area versus a cut area. Again, it's going to largely depend on that response of the plant community, and I think that's going to dictate your long-term response more so than what type of treatment you had. It's how's that treatment going to affect that plant community, and how's that plant community going to change over the long term, and then that's going to dictate your runoff and erosion processes, and those two are linked. And increased infiltration is probably going to affect your soil water, which I think Bruce Roundy talked about in a talk, another talk in this series, and that's going to also affect your plant community in a positive way. So the two are linked, but again, it's associated with those long-term changes in the plant community and the soils, and I really don't think we know the answer to that.
Okay, thanks. That was the last question for the moment, so if people are typing up more questions, I'll submit these three polls, very brief polls, quickly. And then to answer the question about the webinars, a recording of this webinar will be sent to you automatically through the GoToWebinar Citrix Online system tomorrow, but it will also be posted on our Great Basin Science Delivery Project website by the end of this week. And on our website are also all of our past webinars from this series, if you're interested. Okay, just 2 more polls. Thank you so much. And I have another question for Jason. James Gatsky, I hope I said your name right, asks, in the phase 2 to 3 sites, what was the biomass of the trees? Did you notice any differences due to biomass load?
That's not something we measured as part of the hydrology study, and I'm not sure if in fact it was measured by any of the other disciplines as a part of the SageSTEP study. But I do believe Robin Tosh and some others have done some work on that, so he's probably the best contact to answer any questions about biomass differences. We were mainly looking at how the plant community changed, what the understory cover makeup was, and then mortality of shrubs and things like that to get at what phase we were in.
Okay, so James, I can send you Robin Tausch's contact information after this as well. Okay, and then one final poll question. All right, well, Jason, I don't see any further questions. So, again, the webinar will be sent to you through the GoToWebinar system, and also you can find it on the Science Delivery Project website. And if you have more questions regarding this webinar or other topics, please email or call me at any time. And we can even follow up with questions on this webinar too if you thought of questions after the fact. So thank you very much, Jason, for your presentation today. I really appreciate it.
You bet.
All right, and thanks everyone for joining us. And have a great day.